Okay, I will now take over again. We have now finished the technical part of the tutorial, ranging from the CRAN perspective, going on to the multi-cloud radio access networks, where we distribute the intelligence across multiple cloud instances. Furthermore, after that, we went into the hybrid cloud and mobile edge computing frameworks, where we also take into account the computation perspective within the networks, treated interference management with rate splitting and common message decoding, and also talked about a specific XR application where we use device cooperation and cooperative NOMA frameworks. And the last presentation was about the AI-based robust communication and computing. And we now take an outlook to the future research directions of the field of multi-tier computing within decentralized 6G communication networks. By that, we have decided to tackle 5 different outlooks or directions in this regards. First of all is what if we upscale the network and then single cell networks, just like an analogy to the transition from CRAN to multi-cloud RAN. What happens in the multi-cell setup with the previously discussed DNN-based approach? Then we also go into the direction of decentralized learning. So when we extend to the multi-cell setup, how can we decentralize the machine learning algorithms? Beamforming and device association, then non-terrestrial networks, and then in the end, we also talk about resilience in more details. So first of all, talking about multi-cell extension. Checking the previous setup, we had a single base station serving some number of users with uncertainty injection by training the deep neural network for the resource allocation. Now, if you want to extend this to a multi-cell network, for example, we can integrate multiple transmitters of potentially heterogeneous type. For example, here we have a large coverage area, high altitude platform, which we can see here, and maybe some base stations which have a lower coverage area. Now, this has some similarity to the previous section's figure, where we only had one base station that was responsible for managing the resources of its area. But in this case, we have multiple cells, and of course, there is a link between. We have interference between them, we have interaction between them. So this needs to be tackled. What we can do by that is, of course, extend the network coverage, have much more cells, much larger networks, and scale up our approach. And yeah, as I mentioned, this is a scalable solution due to multiple extendable management and access instances. So we could place more base stations here. We could go for the UAVs at the edges, or place more hubs, perhaps, as an idea. As I've mentioned, this could introduce heavy intercell interference, and we need some level of coordination between the management instances to manage this type of interference. Now, when we extend this network, we, of course, will have multiple distributed agents that, of course, on their own want to serve the assigned network participants' needs. And the idea is now that we could utilize some concepts from decentralized learning, distributed intelligence in this case. And the idea is that multiple entities solve a global optimization problem using localized computations collectively. By doing so, this is a low complexity solution for example, large scale networks. And an idea here is to use federated learning for collaborative AI model training. And the idea in federated learning is, of course, we have a server that coordinates the training of a global AI model. And we have local learners. For example, in this case, these are devices. These could also be our base stations in the multi-cell setup. And they do the local learning based on local data sets. And we have some level of cooperation towards the central server for learning. And in this case, we see that there's an opportunity to extend the federated average, famous algorithm, to account for the considered system model. And in the federated averaging algorithm, we have different phases. So first of all, we would broadcast the global model, and then we do the local model updates on each device, and then aggregate again in the end these models. Now, what we have here is we have a centralized parameter server. We can still do the local learning and account in this step for the interference among the cells. Initial experimental performance by our side showed that, of course, the decentralized learning is performing worse than centralized learning, but it is now a challenge to fix this gap, to come close to the centralized learning perspective, to have a practical algorithm which also performs close to the theoretical upper bound. Now, in terms of managed resources, we have seen that the previous setup manages, of course, the transmit powers, the computation powers, and the computation allocations. But if we extend this network, for example, to the multi-cell setup, perfectly we can find good quality transmit and computing powers and computation allocations, but would need to have coordination between the cells. And one of the most important parts, we have to consider the device to cell or device to base station association. There's a typo here. So which cell is serving which user? This needs to be determined, and this is a resource that needs to be managed. Furthermore, for a more sophisticated communication perspective, we, as previously also talked about in the tutorial, have the opportunity to do beamforming. And currently, this is based on state-of-the-art techniques. We use, in this case, zero forcing beamformers, which are, of course, unflexible to different network deployment cases and not always the optimal choice. Therefore, considering optimizing the beamforming vectors to even have more benefits out of this system and improve the performance furthermore becomes an important factor. So let's talk about non-terrestrial networks. So the current network setup could be extended on by utilizing ideas from the non-terrestrial networks, NTN, and that could be the integration of high-altitude platform stations or satellite communication. This has some advantages. Of course, first of all, we have the global coverage. We can ensure the connectivity in remote and underserved areas where, for example, terrestrial networks are impractical. This also has the idea of disaster recovery. So we could provide reliable communication during natural disasters when terrestrial networks could be compromised or break down. Furthermore, we have enhanced connectivity and also an additional layer of network infrastructure, and thereby we can enhance the resilience through redundancy. Of course, this comes not without costs, so we have significant investment required, which is needed for the satellite deployment, maintenance, and the ground station infrastructure. And these satellites have issues like higher latency compared to their terrestrial networks due to just the long distances that the signal must travel. Next in line, let's talk about resilience. Resilience was always talked about within this tutorial, but not really have been defined. And here we check the ITU document here for the IMT 2030 framework, which is 6G. And they define that security and resilience should be by design incorporated into the 6G design. And this is the text from the recommendation. What is resilience for them? It's to continue the operation during and quickly recover from disruptive events. We defined the resilience as a system's capacity or a network's capacity for absorbing a disturbance and reorganizing to retain the network's essential functionality. In the original, resilience roots back to a Latin verb, which is resiliere, which means to rebound or to recoil. And yeah. Now, the idea of resilience is that we have some functionality. For example, this could be quality of service or throughput or worst case delay, depending on the applications we have discussed in our tutorial. And what happens now is that at some point in the time, we have an error that appears. And now the system tries to maintain the functionality during this error. So that means to keep up this, for example, throughput plot as high as possible and as long as possible. Furthermore, the system needs to adapt to this erroneous influence and then hopefully recover the functionality in a timely manner. This is related to different phases. We have the anticipation, which prepares for an error. Then we have the absorption, so how well would the network absorb the error. We have the adaptation, how good are we at adapting to the new circumstances. And the recovery refers to how long does it take us to come back to let's say, a normal state. In this case, this is shown for example, different criticality levels. You could think of 6 different 6G use cases, which could, for example, be safety critical, and especially for those use cases, the resilience of the network and the robustness is of paramount importance. One thing is that resilience is not the same as robustness, and rather robustness is one partial aspect of resilience. And resilience is a much, let's say, bigger concept. So from the resilient network operation perspective, we want to make sure, we need to make sure in the future that resilience is considered in every part of the network design process. In our tutorial, the discussed designs are robust to uncertainties, blockages, and interference, as we have shown in the previous sections. And also we introduce redundancy and diversity, which is crucial for resilience to be implemented within the network design. However, redundancy and diversity may lower the overall efficiency of the network. We have also talked about energy efficiency and sustainability. And the timeliness of remediation and the recovery process is important and has not been considered in a metric before. On the right-hand side, we have an example of, let's say, part of the 5G protocol stack with some of the components of the Open RAN Alliance included, for example, the OCloud and the service management orchestration block, the RAN intelligent controller with non-real-time and near real-time aspect, and some of the protocol stack, RLC, MAC, file layer. And what we want to note here is that resilience, for example here, this plot, and maybe here, some further resilience aspects need to be considered in every part of this protocol stack, in every part of the network design. Okay, if you should have further questions on the future research directions, then feel free to ask them. Otherwise, we will continue with the conclusion by my colleague.